an R here, and we connect. Can you hear the little voice?
Yeah.
She's super cute. She's the daughter of two physicists. Poor thing. But apparently she likes math. Or they want her to like math. Yeah, she's super cute.
How old is she?
She's 5 now. She's 5, amazing. She grew up so fast.
Hi.
Nice to say hi.
You're leaving already.
To have lunch.
Ah, nice. Have a good lunch then. Okay, so this is, we connect the linear one with the angular. Alright, what else did we see that was really new from chapter 8? Torque. Torque is really new. Well, torque we said, like, there are two equations that I can use to write the torque. Either the lever arm, the funny definition for the lever arm, multiplied by the force, or the distance between the x of rotation and the force, and the perpendicular component of the force. So we need the torque when I want to do a rotation, when I want to get angular acceleration. Okay, this is the definition for the torque. But we said torque is also analogous to a linear quantity, which is the force. Force was ma. Okay, so torque. What is torque? If I use this analogy, is again inertia, but a different kind of inertia. What kind of inertia? Moment of inertia, rotational inertia, which is that I. And for the acceleration, I'll put the angular acceleration. So still, there is an analogy there. This moment of inertia depends a lot on which object we're dealing with. There was one that was an easy one when I had a rope and a little ball at the edge and I'm rotating that. What was the equation for that moment of inertia? That's the only one that you need to know. All the others you just get from the table. M, the mass R squared, right? So this is the one that I said we should know. M R squared. Good. One more equation that was useful. Let me put it separated. Something that you already knew. That the velocity from chapter 5, using the velocity is 2 pi r divided by the period, which is 2 pi r multiplied by the frequency. This kind of equation, if I want to use for the angular velocity, we also found one to connect the angular velocity with the frequency. What is the equation?
Velocity over r.
Okay, which is here already.
Which equals 2 pi r f.
So
r, which is
2 pi
f.
frequency. So this is not really new, you can derive it. So let's mark what is really new from chapter 8, that this one is new, this definition of torque. The rest comes from analysis of the derivation. Okay, so now we are going to solve that problem, the first one on top. So don't get confused, there are two problems here. The top one is one, the bottom one is another one. Okay, so the top one is what we have. We have a pulley. So this pulley, it's inside, there is like a rod, and we have this pulley around, okay, rotating. Okay, and it's rotating because there is a force. And the force is there, Ft, and they give us the magnitude of this force, 15 newtons. But because it's rotating around this rod, there is also friction. Since the pulley is touching the rod, there is friction. There is a friction force trying to go against the motion. And they were nice, they give us already the value of the torque caused by this friction force. So the frictional torque, they said, is 1.10 m and newton, meters and newton. Now this is against the motion, trying to go clockwise, so I'm going to put this minus sign. Remember the convention, right? Clockwise is negative. Okay. They also gave us the radius of this whole big pulley. This radius here. This radius is 0.33 meters. So with this R, with that force, I can get what is the torque caused by that force. What is the torque?
Force times 0.23 meters.
Right. You see that we are not worried here about angles because the radius and the torque, the radius and the force, they are already perpendicular. So this torque is just the force multiplied by the radius. So I didn't worry about any angle. So here it's just the 15 multiplied by 0.33 and you get a number. Okay, so this is the story of torques. What else we find in this problem? What is the
Force of
question?
friction.
Yeah, so it's here already the frictional torque.
We
They
have
gave
that.
us the value of the friction torque already.
Oh.
Very good. They also gave us I. Well, the question is I, sorry. So they want us to find I. They want us to find the moment of inertia. But they give us another piece of information that's really.
Mass,
They gave us the mass. I'm going to put the mass here.
which is helpful.
They said that this pulley is accelerated uniformly from rest. From rest means initial angular velocity 0 to final angular velocity 30 radians per second. And it takes 3 seconds for that.
So we can find the acceleration.
Very good. So all this combination of information here, well, is to give us the acceleration. So from here, we can get the acceleration, the angular acceleration. How?
Divide.
W equals W naught.
Well, W final minus W initial all over T.
Yeah, you can go like this, which is the same thing if you want to go straight to this equation. These are the same. So either this equation or this equation will give you the angular acceleration. They're the same equation. So we also have the acceleration.
And we have the force. But why do we need all this? Can't we just say mr squared and find the moment of inertia that way?
Okay, let's think about this. Mr squared is not for this complicated rigid object. The mr squared is I have a little row and I have an object around here and I'm rotating it. Okay, so this mr squared for this kind of scenario.
So we can't assume that the angular velocity and angular acceleration are the same.
Angular velocity and angular acceleration, these are two different things.
I mean,
right?
that they remain constant. We can't assume that.
You can assume that the angular acceleration is constant because they tell us the angular acceleration is uniform. They say accelerates uniformly. So alpha is constant. I just said that I cannot use this equation here because this is for a different problem. Remember, we have a list of moment of inertia.
Yeah.
You could try to go to that table and see which object looks more similar to this one. The pulley is more or less like a cylinder. It's more or less like a disc with a, so it's more or less like a cylinder. I'm going to put this one here, since it came to your mind. I'll put the cylinder, the moment of inertia of the cylinder. If you go to the table, is 1/2 of mr squared. I'll keep this here as a possible alternative.
Sorry, which table are you referring to?
Look at, okay, I'll show to you, but it's one of these ones. This thing.
Oh, that's what it's for.
Okay, so this is the cylinder. So this is 1/2 of mr squared. If the object was a sphere, it would be 2/5 of mr squared. So it depends on which problem we are solving.
Okay.
There is the hoop. The hoop shows up in one of your problems in the web assignment. We'll see. So either the problem will give you the moment of inertia, or will tell you look at the table.
Why is it different if they're all going in the same?
What is the moment of inertia? It tells us how the mass is distributed. Remember this?
Yeah.
That we talked too quickly last class. And so this object and this one have different moment of inertia. This one has most of the mass very close to the axis of rotation, so the moment of inertia here is smaller than here, where the mass is very far from the axis of rotation. Yeah, we passed too quickly, so I'll tell you a little bit more there. Yes, because the moment of inertia depends on where the mass is. This is not depends on the each object has a different moment of inertia, but see, like the little object at the edge, the further. So this is the rope, and I have an object. If I pick another rope here, the moment of inertia will be bigger. So the further I am from the x, the bigger the moment of inertia.
Why does moment of inertia replace mass in our equation?
Because we are to rotate an object, it doesn't matter just the mass of the object, but also how the mass is distributed. Where I'm applying this force, where I'm applying this matter.
What's the difference? Like, what's the torque of friction and the torque of T? Like, what's the difference?
So the torque of friction is the one caused by this force of friction.
Okay.
And this other torque that I wrote is the one caused by this perpendicular force, which is someone there trying to rotate the tool.
Why is there a torque of friction?
Because the pulley, so this is the pulley, okay? And there is a rod here. So the pulley is touching this rod. So it's trying to rotate, but the friction is preventing it from rotating.
Okay.
Okay, so the moment of inertia, and we will talk a lot about the moment of inertia, it depends on how the mass is distributed. Remember this problem that we solved very quickly, but it was the same rod, and I had two objects at the edge. This one had one moment of inertia. Let me show the number. This one, the axis of rotation is here in the middle where my fingers are. Okay? And I got this little moment of inertia because the masses are not too far from the center. Now below, how did I rotate? Like this. Okay, so I just changed the axis of rotation. Now the mass one is here and the other one is far away. So now the moment of inertia for this one is much bigger. Okay, so the further the mass is from the axis of rotation, the bigger the moment of inertia is. And what does it mean? Bigger moment of inertia means it's more difficult to start moving the object. And it's also more difficult to stop it.
If you think about it logically, the further you are away from an object, like if you have a lever arm, the further you are away, the easier it is.
For
Bigger-
us,
For us.
the force, for the torque.
For the torque, exactly. So how does that apply here?
Because what we need, let's see. This is the equation. Okay, so the bigger the moment of it, okay. If I apply a big torque, I may not, it's similar again to the inertia of the truck. Let's see.
I think it's saying that if your moment of inertia is greater, the torque required is greater.
Exactly. The same thing when we had the force. If I had a big truck, I might get a little acceleration for the same force that I apply for a little bike. Same story here again. Depending on the moment of inertia, I may have just a little ping pong ball that I want to rotate. Or I want to rotate a huge sphere. So then there is the mass involved and also how this mass is distributed. It's all contained in the moment of inertia. Yeah, Laura? No?
No, I just figured. Yeah, but I still don't understand. But I'm still right.
Okay.
If it's further away, you should have.
The force applied is good. Further away we go. But the mass being further and further gives you a bigger moment of inertia. You have to move all this mass out that is far away from the center, from the axis of rotation. You have to move all of that. While if the thing is already concentrated around the axis of rotation, it's not going to be too hard to move it.
Oh, because I'm thinking of it in terms of levers.
Yeah,
So
you
say
think
you just
about-
have a giant ball, it's easier to move that giant ball if you're standing close to it than if you're trying to reach and.
Imagine if you're holding a plank with someone sitting at the edge of the plank versus someone sitting in the middle of the plank. Which one's going to be harder to lift?
Yeah.
Okay.
Exactly.
Got it.
Like the carousel. If you had to rotate the carousel, if the child is at the edge or is the child already at the X, it's easier to rotate.
So no levers in this situation.
The lever is coming here. Okay, the further I go, the more effective will my force be.
And okay, and since you have a bigger torque, then you have to have a bigger moment of inertia anyway.
Yeah, then
For the same acceleration.
for the same acceleration, I need a bigger torque. Yeah. If the moment of inertia is bigger, I need a bigger torque.
I got it. Thank you.
Go on.
How did you look at the problem and decide that the first thing you were going to do is try the first equation, the force of
So here was just this was given to me, so I didn't do anything. And here they gave me a force. They gave me this radius. I computed the torque. That's it. I just computed the torque for each force. I'm just here was just accumulating all the information that the problem had given to me. So they gave me the frictional torque. I put there. They gave me enough information to compute the torque of that force. I computed. So far, I haven't solved the problem. They also let me erase this story now. They also gave us the change in angular velocity and time, so I was able to get to the acceleration. So far, I haven't solved the problem. I just accumulated information. Now comes this question. The question of the problem is, what is the moment of inertia? And then Odeya came with a very good idea. She said, well, don't you have an equation for the moment of inertia? Can't I just use an equation for the moment of inertia? And then we were thinking, okay, which is the object that we have here? We said, no, it looks like a cylinder. Here I put the equation for the cylinder. I'll put it here, and we'll try to get a number here. But is there any other way that we could try to find this moment of inertia?
Yeah.
Torque.
Torque equals moments of inertia times angular acceleration.
Very good. So let me write this here. Torque, and what we need is net torque. Just here, I have net acceleration is NA. Net torque is I alpha. Okay, so net torque has I alpha. I is what I don't have that I'm trying to find. Acceleration, we said yes, we do have information to get acceleration. And net torque, do I have the net torque?
well,
Yes.
you add together
Yeah, it's the sum of these two. So this number minus that number gives me the net torque.
which are minus which one?
Well, this is positive, this is negative. So here I have the net torque, I have the acceleration, we can find this I. Double check that you get the number. You got it? Yeah.
In terms of subtracting the friction torque, I guess, did you, should we take that negative into account when subtracting, or that's already taken into
It's already taken into account. Okay? So I'm adding all the torques. Some are positive, some are negative. Remember, how do we know which one is being clockwise, which is counterclockwise? Okay, so this is counterclockwise, the friction is clockwise. So okay. So some people already got it, right? And the number that we have there in the answer is 0.385. What is the unit for moment of inertia? Kilogram from the mass, r squared, so meter squared. Okay? Kilogram, meter squared. So this is an exact solution coming from the net torque. Okay? So this is exact. If we try to use Odeya's idea, which was a pretty good idea, so if I go straight to an equation that we found in the table, looks like the pole is similar to a cylinder, so I'm going to try to use this
What
equation.
was our angular velocity again? We found it from the.
It's 30 divided by 2, so it's 10 radians per second. So if I try to use Odeya's idea, I put 1/2, the mass is 4 kilograms, the radius 0.33 squared. What do you get for this number?
I'm sorry, Quick question.
Yeah.
For the net torque, you add the two torques?
Yes, but one is positive
And negative,
the
right.
other one is negative, so it's a subtract. You get it? So maybe someone can try to get the number that we get if I use this equation. It's not, but it's 0.2 something. 0.2 what? 178. 1/8 upward. Okay, it's not the same, fine, but it's not completely different. It has some similarity. Why it's not equal?
It doesn't take friction into account?
No, okay. Friction I already took into account here, and here just use the equation for the moment of inertia.
But I'm saying the equation for the moment of the
It's not exactly the same object, that's for sure. This equation here is for a cylinder, it's homogeneous, where the mass is uniformly distributed. The pulley is not uniformly distributed. What is the difference? What is the shape? What changes in the pulley with respect to a uniform cylinder? The pulley has a hole in the middle to start with. It has a hole right where the axis of rotation is. And then I don't know exactly how it's distributed. So it's not exactly equal because it's not exactly the same shape, but it's similar. Why do you think we got a bigger moment of inertia for our pulley? If I compare with the uniform cylinder, why this one is bigger?
Because the axis of rotation is different because of the hole.
Because of the hole, you're in the right track. Go on. Exactly. So we have more mass further away from the axis. That's why this moment of inertia is bigger. Got it? Right in the middle, right at the center, there is nothing. There is just a hole. Okay, so the further the mass is from the axis, the bigger the moment of inertia, and that's what I get a bigger number.
So say our hole is bigger, then our moment of inertia is going to be bigger.
Yes.
Which is why when we have the equation of the ring from before, it's just mr squared. It's not half
Good
mr squared.
point. Yeah, very good point.
Okay. That makes so much more sense.
What equation from before?
For the
MR
little mass
squared.
that is just at the edge, we don't have a half.
It's all one big hole in the middle.
Yeah.
So you have to take into account all the mass, not just half the mass.
But if it wasn't something we could
If the problem had told us we have a uniform cylinder, then we could use that.
It's 'cause it's not one big
Okay, so now let's make this problem a little bit more difficult.
hole. There's more space for the mass to be spread out.
Look at that. Now I have the same pulley there. Friction, force. But what I'm going to do is, I have now a rope here attached to a bucket.
Oh yay.
There you come the bucket again. Okay? Very
Yeah,
similar
very
to what we
scary.
solved in chapter 4. We had a bucket attached to a box, and the box was translating. Here we have a bucket but attached to a pulley. So now I have rotation. Okay. The bucket has a weight. Because of this weight it falls. Through this rope we have tension force, trying to hold the object but not enough. And this tension force is here, action and reaction, rotating the pulley. Let me choose a reference frame. I'm going to choose downbeam pulse. How are we going to solve? Just as we did in chapter 4. Equation for one object, equation for the other. So here at the top I'll put the equation for the pulley. Here at the bottom I'm going to put the equation for the bucket. Let's start from the bucket. The bucket you're very much familiar with, right? How do we write the equation for the bucket? Let me put this object will fall down and the acceleration is pointing down.
So it's mg is positive.
It's mg minus ft equals mi.
Very good. A is positive, right? So this is the equation for the bucket. How about the pulley? What is the equation for the pulley? For the pulley, we don't play directly with forces. We play with torques. Same idea, right? But torque. So sum of all the torques will be I alpha now. Laura?
Why did you write it like with the force of tension going both directions?
Action and reaction, just as we did in chapter 4. Remember that the bucket was falling and trying to carry the box. So it's trying to carry the box. So here it's trying to rotate the pulley, and there is a reaction. The pulley is trying to bring the bucket up. So it's right. Remember we had here the box attached to the bucket. So the bucket was pulling this box. The box was reacting and trying to pull the bucket.
And we're gonna use the reaction.
Yeah. So this is action and reaction. That's why I have.
We don't use both of the force of tensions in our equation that we just wrote.
Yeah. So this this is the bucket pulling the pulley, and this is the pulley pulling the bucket. So equation for the pulley, who got it?
FTR.
All right, very good. So I'm putting here FTR is the torque for this force.
And is it negative? No, it's positive.
Right.
Because it's going
Remember
down.
the convention here,
Right.
positive. Okay, what else do we have?
Minus the friction.
Minus the friction torque, and this number is given to us.
It is?
Yeah.
Yeah, it's the 1.10.
It's the same one from
Still
before.
the same from before. This is the torque, sum of all the torques. And sum of all the torques, net torque is equal to I. And the I we already found. Okay, I'll mark what is the unknown of this problem. They want to know what is this angular acceleration. They want to know what is this linear acceleration.
And do you do, meaning we have torque friction as a negative number, so do we keep that negative, meaning does it become plus torque friction?
No, it's already, this
It's
minus
minus
sign is already
Oh, it's
taken
already
account.
part of it. Okay.
Right? One is trying to cancel the other. The friction is always trying to go against it.
Are we looking for FT?
We're looking for-
Very good. How am I going to solve? I want the accelerations. The FT is on my way. It's the only thing that I don't know in this story. I'm going to isolate it and plug into the other equation. So I'll isolate from here. You can isolate from any other. I'll isolate it from here. So from here, I find that FT is equal to mg minus ma.
So
Alright?
it's mg minus a.
And yeah, you can put m and parentheses g minus a. So this whole thing, I'm going to plug into that equation. Just as we used to do. Alright, so then I have mg minus ma multiplied by r minus the friction torque equals to I. I want to find alpha, I want to find a, and am I in trouble?
No,
Yeah,
because
two.
yeah, but you know that alpha equals r times a.
Right.
Sorry. A equals r times alpha.
Very good. It looks like I look at this equation, I'm getting desperate, oh, I have two unknowns, how can I solve this equation? But remember, the linear acceleration is r alpha. So this linear acceleration is just r and the angular acceleration. So now in this equation, I have just alpha. Everything else are numbers that I know, so I can find it out.
Shouldn't you just plug in mg minus ma if FDR should be negative? Shouldn't it be opposite sign?
Here,
Yeah, because it's action and reaction, so one FT goes up and the FT goes down.
What?
Okay, good
What?
question
What?
what she asked. No, look at this. Good question she asked. She looked at this frame and she said, wait a second, here you fine, you put the FT is negative, but here shouldn't the FT be negative
Why?
because of the frame?
But wouldn't the F to be positive?
Well,
It's pointing down.
for the direction according to this frame, this is negative and this is positive.
Right.
Yeah, but even that, here. Yeah. But even when we are writing this equation here, don't worry about this frame because this is not an equation for force. This is an equation for torque. So forget there. What you're going to do is an equation for torque. So counterclockwise will be plus, clockwise will be negative. Okay, you don't look at if the force is plus or minus.
Oh, because the equation that we put in the bucket is based on Ft being negative. So when we plug it into the Ft being positive, shouldn't it be flipped? Is that the question?
When I'm writing those equations, I'm already taking all the directions into account here. So the number that will come out here is just a number anyway. No? So, but equations for forces, I have to take into account the frame. Equations for torque, I have to take into account the convention. All right.
What's the mass? 4 kilograms.
Okay, so the mass is not given, but they gave us the weight, didn't they? They said that the weight is 15 newtons.
Oh, so 15 divided by 9.8.
So yeah,
Why
so
can't
even
we
though
do
the
MG
mass
then?
is not given explicitly, you know that the mass of the bucket is 15 newtons divided by 9.8.
We don't even need that though, because we're looking for mg anyway.
We need for the MA.
But it appears here.
Okay, why divided by 9.8?
Weight is mg, right?
Okay.
So if I just want the mass, I divide the weight by g.
Oh, I see.
Okay, so anyone gets that number for alpha 6.98 radians per second squared.
How would you deal with the fact that you still have alpha in parentheses?
Everything there are
Do you want to
symbols, but
distribute
numbers. But if you want, you can play a little bit more with it. So
I know, but
M
you still have it in parentheses.
minus m r squared alpha.
You distribute it? So we would have to distribute alpha, no? Because it's still in parentheses. What?
So everything there is just numbers. You can just put the numbers. But this equation, I'm writing it here in case you want. Huh? So
Right.
mgr, m, and now all a's are alpha. So m r and another r squared alpha, friction and I alpha.
Got it. And R is 0.33, right?
I is
R is
0.38.
0.33. R.
R is 0.3.
Okay. Just wanna follow.
Or you don't need to do all these steps that I'm doing. It's just if you want to simplify all the way to the end. But anyway, this is the answer. This is the answer just for the angular acceleration. But that's not all. We still need what? This is the angular acceleration. What else did the problem ask us to solve? The linear, right? So we also have to find this a here. So I just multiply this number by 0.33.
Just do what? To get the R.
The R we already have.
Right.
After we got to the angular acceleration, we can get the linear acceleration. We have the questions both alpha and angular and linear acceleration. Has anyone got this one? I think it's 2 or 3 or 2 or something. But once the linear one multiplied by 0.33, what is the value? 0.3 is not 3? 2.3? Okay. No, it's not? You didn't get that? This one you didn't get? What did you get? Completely different or? You got it. You got it also. So, silly thing in
Radians?
What was the answer they were supposed to get?
it's here. It's in the book.
Oh, radians, though.
But that's
How do you get radians?
We're not calculating angles here though.
There is no way.
You get it anyway.
Okay, so it's just a playing with the calculator properly. You should. Can I erase? So this is a connection with chapter 4, torque and forces. Now I'm going to continue with our analogies. And I'm going to connect with chapter 6. Remember chapter 6 was energy. What was the equation for, this is maybe too much. What was the equation for kinetic energy in chapter 6 that you learned? 1/2 of mv squared, right? So this was when you had the translational motion. So this is linear kinetic energy. What do you think I should write for angular or rotational kinetic energy?
1/2 of omega squared.
Say it again.
1/2 omega squared.
Okay, very good. Omega squared is what is going to show up there. Let me rotational kinetic energy. It's going to be
Oh, with mass also.
yes. But what is should I put in place of the mass? The I, the moment of inertia. So I omega squared. That's it. Okay, so it's not too bad. Looks like it's something completely new, but it's all right.
So do we always replace mass with the moment of inertia with
Yeah.
rotational?
We are removing the linear inertia with the rotational inertia. Mass is when I have just the translation.
And when we have both.
Okay, this is what I want to say now. Now if I have if I had an object that was just translating, this is the kinetic energy. If I have an object that is just rotating, this is the kinetic energy. But suppose I have the bike wheel that is rotating but is also on the floor, translating. So I have a combination of two things. I have the translational motion, so I have this linear kinetic energy, and I also have the rotational part. Okay? So now I have a sum of both. Yes.
And you're not realistically, if a bike is biking down the street, there's going to be friction. You're just disqualifying
There
that.
could be friction. There could be friction. This is just the part, the kinetic energy. There can be losses involved. There can be losses in the mechanical energy.
So if it's not conserved, what will the equation look like?
The equation for kinetic energy is always this. Now I can write in the equations of conservation of energy. Then I would have to include also losses. But this is kinetic energy only. So let's try to solve a problem very similar to what we had in chapter 6, but involving now both. What is the problem? Again, we start with incline. And here I have a sphere. The sphere initially is at rest, high up, at this height, big H. So this problem is always simple, there are no numbers. Okay? So high up here, someone is holding the ball. It has only potential energy. Then I let it go. It's going to roll down. Okay, so it's going to roll down, so it has translation and it has rotational involved. And what we want to know is when it gets to the bottom, what is the velocity, the magnitude of this translational velocity.
Sorry to go back to the equation. Originally our kinetic energy equation was mv squared over 2.
Right.
But why here do we need the mv squared over 2 and plus rotational kinetic
Because
energy?
we are also rotating. We are not just translating. So the box, when the box goes from here to here, it has only 1/2 of mv squared. But now it's a ball that is also rotating.
So is any time that we use rotational kinetic energy, do we also have to take into account linear?
Depends. If it's the ball rotating in the air here, if it's not changing its position, then it's just a rotation.
So when it asks for the speed, is it just asking for the linear velocity?
In this case, yes. Yeah, they are just asking us this speed. If they wanted to be more, if they wanted the angle, they would say, what is the angular velocity, or what is the magnitude of the angular velocity? Okay, the speed here is just the linear. Okay, How are we going to solve this problem? Old problem from chapter 6, conservation of energy. I started with just potential, okay, so I'm going to write it there. The mass is big M, GH. Okay, so that's all that I have initially. There is no friction in this problem, so conservation of mechanical energy. Starting with potential, the potential will be transformed into kinetic. What should we write for kinetic?
We need 1/2 mv squared plus 1/2 moment of inertia times squared times.
Because we are rolling, no? It's not just translating, we are rotating also, so we have the combination of both. And I want to find just V. How can I find just V? There is something that is given to us if you go on reading the problem. They say, look, this is a solid, uniform sphere, so the moment of inertia for that is 2/5 of mr squared. Okay, this is given to us. Okay. I want to find an expression for V, and I want an expression for V that involves only G and H. Okay? I want V depending only on G and H. I don't want to see mass showing up there. I don't want to see omega showing up there. So what would you do?
Well, if you,
We can cancel many things.
you can cancel this, yeah, for sure.
Yes. If I put this there, right? Okay, so if I use this equation, I'll substitute this I with that equation. 2/5 of mr squared. So with that, I can cancel the masses. I see mass here, mass here, mass here.
Why is mass capital?
You can give any, you can put capital. What else can I cancel? Here I see this half and I see this 2/5. The 2, right? I have 2 at the top and 2 at the bottom. Oh, if you don't see this yet, that's fine. I'll keep it like that. Remember what I
So
said?
it's 1/5.
Yeah, it's going to be just 1. Remember what I said? I want an equation for V that depends only on G and H. I see that omega on my way there. How can I
Omega
remove this
times
omega?
r.
Right.
Because you're multiplying it by r anyway because it's mr squared.
Okay. Okay, you're correct. So, but I'm going to write this equation there. Okay. Instead of writing omega, I'm going to write V divided by R. Okay. So this, I'm going to write V divided by R squared. So let me put everything here. So I have GH equals to 1/2 of V squared, and then I have 1/2 of those 2/5 that remain. I have R squared, V squared over R squared.
R squared cancels out.
All right, so let me get rid of this R squared.
1/2 times 2/5.
Now
just
the 2
1/5.
is very explicit, right? We can get rid of this 2.
Take out the V squared.
Now, so let me rewrite this equation here. I have, let me write it V squared over 2, and the other one is V squared over 5. How do we solve fractions like this?
Common denominator.
7V squared over 10.
Very good. 7V squared over 10, let's get, but what was the problem? Where did you go?
I'm good.
You got?
Yeah.
Okay.
Yeah.
So the common denominator is 10, right? 10 divided by 2 gives me 5. 10 divided by 5 gives me 2. You remember this, right? So this whole thing is 7V squared over 10.
Equals G.
So now let me put all together. I have GH equals to 7V squared over 10. Tell me if there is something that you missed. You could just put in the calculator this 1/2, this 1/5, and play with instead of fractions the real numbers.
And this only works for a sphere.
Yeah, this moment of inertia is for this sphere.
And
So
then
from
root-
here I can get the v. The v is going to be square root of 10gh divided by 10. So this is our v. Oh, sorry, there is a 7, huh? And this result is also in this. So this problem that I solved here is for this sphere. There is rolling. So that's the v that I found. But suppose my sphere was not rolling. It was just sliding. It would be hard to have a sphere only sliding, right? I could put a ring underneath to hold it, or think of a box just sliding. So what I want to know now is, if I had the same problem, but instead of rolling, the object was just sliding, what would change in this
You would
equation?
only have 1/2 mv squared,
Only this.
and then you cross out the m's, multiply by 2, and square root. So square
Alright.
root of 2gh.
So everybody sees that, right? If I'm just sliding, this part does not exist. I get the v is just the square root of 2gh.
But like if you put a
Cross out
cylinder
the
in there,
m's.
the only thing that would
That's
change
like
would be
two
that
six.
instead of using the equation 2/5 mr squared, you would use like the 1/2 mr squared.
If I had a cylinder rolling, yeah, so then you would change the I.
Okay.
But there at the top, I don't have any. It's not rolling. I have the box just goes like this, just slides.
So any shape that would just slide, you could just use that.
Yeah, because the rotation doesn't exist.
If it's just sliding, there is a force of friction.
Any problem here also there is friction. There is in real life, all of these problems have friction, but I'm ignoring friction. I'm saying the mechanical energy is conserved. Now my question for you is, which one is larger?
And this is for any sliding object. It
Yeah.
doesn't have to be a sphere.
Yes, any sliding.
Because we didn't need to use the moment of inertia.
Which one is larger and why?
The top one's larger.
The top one is larger and why?
Because we're not taking into account friction. Normally, if you did have friction, then
The friction is an annoying thing, yeah. But remove friction from our lives.
Oh, because you also have centripetal acceleration.
That's the idea. What is going on here? Part of our energy, part of the potential energy, is transformed. It's being used not just to translate the object, but also to rotate. So I have this whole total energy. Part of it goes to the translation. Part of it goes to rotate the
So it
object.
doesn't move as fast.
No. Here, everything just goes to the translation. So all that speed just going to the translation. All that energy just going to the translation. All right.
Wait, so rolling is faster.
So the
Sliding is faster.
the linear velocity that we get at the edge is smaller
Oh, okay.
because I use part of the energy. I had to use part of the potential energy to rotate.
So assuming that there's no friction,
Yeah,
it would
assuming
be
that there is no
faster
friction.
to go down a hill in a sled than it would in a tire.
Exactly. Okay. Now
It
this
feels faster, but
this
it isn't.
equation here you're not going to use. I just put it here in case you get it and catch. Okay. But this is an equation for work. Again,
Oh boy.
just remember doing this
Never
analogy.
escape
Work is force multiplied by displacement. Okay, now I have rotation. So my work will be the torque and the angular displacement. But I don't think you have it.
Force multiplied by what is that?
Remember chapter 4. Work is force multiplied by displacement.
Displacement. Okay.
Now if I want
So
to
that's
know,
a D, really. That L is
yeah,
a D.
yeah, you can
Okay.
call it. And here it's going to be work is torque divided multiplied by the angular displacement. But let me continue with our analysis. Something nice is coming. So this was for energy. Let me add one more. What was the equation for momentum? Now chapter 7, momentum. Alright. So linear momentum was mv. Okay, I want to do the same now for angular momentum.
So I omega.
Very good. So angular momentum would be, now comes a funny letter, nothing to do, but the angular momentum is L I omega.
Why?
The angular what?
Momentum. This is momentum, this is momentum. One is linear and the other is angular.
Why?
The name, the
Yeah.
letter.
Do we use the letter B ever?
B will show up a lot next semester for magnetic. If you want to, you can use any letter. Yes, Laura.
In what action will we see angular momentum? Like if the ball is rolling down the hill?
You will see now. I will show to you a problem where angular momentum will show up. I'm just defining for the moment. Now remember when we talked about momentum and force, we said, oh look, when Newton wrote the equation for force, he didn't really write ma. He wrote that the force was the change in momentum. You remember this?
Mm-hmm.
Okay, so again, continue with our analogy, I'll say that the torque is the change in angular momentum. Okay. Let me come back here. Momentum is mv. Force is change in momentum. Angular momentum is I omega. Torque is the change in angular momentum. You remember this, right? Remember that can we write like this? Well, momentum is mass v, so mass and the change in velocity will give us ma. Same thing here. If the moment of inertia does not change, if the I does not change, I can isolate the I and delta omega delta t. I have I alpha. Now comes something else. Suppose the net torque, go on.
One more time, please.
Okay. Starting from here.
Yes.
So this is how Newton defined force. Alright? And why didn't he write as we wrote? We wrote ma for force. Well, because these two are equivalent. Momentum is mv. Okay, so I put m, changing v, that gives me a.
Not that part.
Now comes same thing but for torque and angular momentum. Okay? So I can say that, well, this is the angular momentum, and I say torque is the change in angular momentum in time. Alright? Same.
Oh.
Now let me continue. What is angular momentum? I and omega. So I change in omega. I change in omega is acceleration. So everything goes in analogy. Tell me again who has problems.
Then why are the units for angular momentum kilograms times meter squared per second and not per second squared?
Angular momentum, you said, okay, let's put all the units. This one is radians per second. Radians we said is not really a unit. This one is kilogram meter squared, right?
Oh, okay, I got it.
Yeah, already?
Yeah.
Anyone has any other question? No?
Can you explain? Sorry, I know you did it already sometimes. How did you get from L equals inertia?
So what
So
are the
this
units of
one, I just P is the equivalent of L when I have angular motion, okay? Okay, and then I come, mass is inertia. I'm using rotational inertia. V is velocity. I'm using angular velocity.
Wait, why is
That makes sense.
inertia?
M is mass. Mass we used to call inertia, right? We said that the truck has more inertia than the little,
Okay.
the little car, the ball, the bike.
And then where does torque equals delta L over delta T?
So, I know this. I'm just telling you. This we already said that torque is equal to I alpha. Okay? Now again from the analogy, I'm saying force was changing momentum. Now I'm saying torque is changing angular momentum. Analogy. And you see that's not bad. Because if angular momentum is I omega, okay, I put I here and I have change in omega. Change in velocity is acceleration. Change in angular velocity is angular acceleration. Alright.
So what are the units of L? It's
Okay, so let's radian per second.
kilograms meters
here.
squared over seconds. Squared
Kilograms meter squared
over
second.
second squared.
Alright. So far so good. Now my question for you is the following. Suppose, okay, so new question here. Suppose my net torque is 0. If my net torque is 0, everybody's with me? If my net torque is 0, it means that I do not have change in angular momentum. Correct? If the net torque is 0, this is 0. You following? You're a bit distracted, I see. Okay. So if the angular momentum does not change, I can say that the initial is equal to the final.
How can we necessarily?
If it does not change in time, so the initial and the final is the same.
Because the only way you could get it to equal 0 is if delta L is 0.
Right.
Because if delta T is 0, it would be infinite. Like, that's not a thing. You can't
Ah.
divide by 0, right?
Yeah. We
Right.
are not talking about the time.
And if-
Time is changing. Okay.
And if delta L and delta T were the same,
So
then
this
it's
is the
double.
final minus the initial divided by delta T.
Right.
And so if this is 0, then this is equal. And when would this happen? When would the net torque be 0?
When there's no
When it's at rest.
acceleration.
Very good. If there is no angular acceleration, if the angular acceleration is 0, net torque is 0, this is equal.
Because the angular velocity stays the same. So it depends on angular velocity.
This is
Sorry, can you explain again why they're equal?
because I already said from the beginning, I summed all the torques involved and I found that net torque is 0.
Okay.
Okay? If net torque is 0, this is the definition of torque, right? So this means that this angular momentum does not change. So there are two ways. This is the nice thing. There are two ways for the moment, the angular momentum not to change. It will not change. Let me rewrite this equation like this. This is the moment, I keep saying, the angular momentum. I naught equals to I omega. Okay? Constant. It's not changing. So if the angular momentum is not changing, the net torque is 0. One possibility, if the angular velocity is not changing, is there any other possibility that you see by looking at this equation that would say that the angular momentum is not changing?
What do you mean? We
If
said
it-
it's not
if
changing.
it's a rigid object.
Huh?
If it's a rigid object, in other words, if the R stays the same and the mass stays the same, then your I isn't changing either.
Okay, if the I
I'm
does
confused
not
about
change,
the question. What are we
oh,
asking?
my question is, there is one way that what they already said is, if the torque is 0, what we have is the angular momentum does not change. How can I make the angular momentum always the same? One way is if my angular velocity does not change. And in the rigid object, that's the case. The shape of the rigid object cannot change. So the angular velocity has to be the same. Another.
If the object's in the middle of a disk, then the moment of inertia would be zero because the r is zero.
Okay, you're in the right direction. How can I conserve? Let me see. I'll explain to everybody. How can I conserve angular momentum? Either my velocity does not change, or the velocity change, but then I have to change the moment of inertia. How on earth can I change the moment of inertia? The ice skater. So let me show to you, and then now you will understand for sure. Everybody has seen these ice skaters. No, it's a beautiful thing. So what do? They are rotating, right? So they start the motion like this with, I'm going to do this if I don't fall. So they start with the arms far away. If the arms are far away, so they're rotating like this. The arms are far away, open like that. The moment of inertia is small or large? Very large. So the moment of inertia is very large, and they are rotating slowly. And then what they do is they close their hands. What changed to the moment of inertia? It gets small, but the momentum has to be conserved.
So velocity increases.
Okay, so when I look at this equation, either the velocity is the same, or well, I can change the velocity if I change the moment of inertia. Got it? So there I come to demonstrate that. And I did this before, so that means I'll get easier and easier. So I'm rotating, and then did you notice that? Did you notice that I spin a little faster? If anyone wants to try, you can. Any volunteer? You
Sure.
all move now.
Do you want to do it? I want to do it.
Go for it.
Yeah? Be careful. Just be careful because it has very little friction. This is like the ice. Okay.
This
So-
is being recorded forever, yeah.
Open arms, and I'll rotate you a little bit. Did you? Yeah. If you want to, you can go faster.
You can
And then as you
go
open the
faster, yeah.
arms, it slows down. Yeah.
What?
Okay, now we're.
Now you're rotating also. Anyway.
It works
Anyone
the
can
same
do.
with ballet terms if anyone does.
All right.
Yes.
So all this to add a new equation to our list here, which is conservation of angular momentum. So let me put this here, and then we are going to solve a problem. So the new equation is this. And we're talking about conservation of angular momentum. The problems are very simple, the ones involving this.
Can we just think of it in terms of mass times velocity? Except the angular terms that we have.
Mass times velocity.
In other words, this
Because there is also the distribution of this mass, no? So if it's far, if it's close, so think about momentum.
I mean, in anything angular, all we're doing is we're replacing mass with I. We're replacing V with omega. Can we just
Yes.
think of it? in
Yeah,
terms
it
of
is
equation?
conservation of momentum. Yes, okay. Now I got conservation of momentum, what we had before, MA, VA, plus MB, VB. Yeah, conserved. It's the same thing here.
Okay.
Now, but we are talking about angular momentum. That's all.
So this isn't a new
And
equation.
but we can change the moment of inertia. So let's try to solve a problem. Let's see if you understand what is going on there. We have a little box at the edge of a rope rotating. Okay? And now, at the middle of this table, there is a hole. So there is someone under the desk, under that table, and the person pulls the rope a little bit, so reduces the radius. Okay, it's all very fictitious. Now you think there is no friction and so on. So we start the motion with this radius. So this is the rope. There is a little box here with a certain mass, and we start with this radius 0.8. And we have an initial speed given to us, 2.4. Now I reduce the size of the rope. The guy is underneath the table pulling it. So the object keeps on rotating, but now with a smaller radius, r2. And we want to know what is going to be this new v. Did you understand? It's like the ice skater, changing the moment of inertia by reducing the radius.
So you just use that.
Yeah, that's it. We're just going to use this equation, so let's write it.
Do we have the mass?
So let's see if we need the mass. So this is the initial equal to the final. Just use conservation of angular momentum.
And we can use mr squared in this
Very
situation.
good. So let's put, for this one is the box at the edge of the row. I'm going to use m r1 squared for the moment of inertia. What else? For they didn't give omega, right? But they gave us v. v1 over r, r1. And on the right, same thing. M r2 squared, v2 over r2.
So if you look at the problem, can you tell that it's not giving us the angular acceleration?
Because
so
they say, let's see, initially revolves at 2.4 meters per second.
So it's not meters per second squared?
That would be acceleration, meters per second squared. If it was radians per second, that would be angular velocity. They put meters per second, that is linear. Okay? Now,
So let's plug in numbers.
the masses cancel, so I don't need to know that. R cancel, and we're going to get to P2. One of the R's cancel, right?
So v1 over r1.
No,
No, no.
r times e.
Yeah.
So the equation that I have now is R1 V1 equals to R2 V2, and we get V2.
Oh, they canceled themselves. R1 canceled with R.
Yeah, these R1 cancel with it.
And we have everything except v2.
Right. The next problem is for, we can talk about the next problem next class. It's the same problem again, but just for a sphere, okay? But I just want to finish this chapter with the last topic, and this is something that is not going to be in the exam, but we were talking about angular velocity all the time. And I never associated with this angular velocity a vector. Never talked about a vector. Just said, oh, it's the change in the angle divided by time, and we just computed numbers. But there is a vector associated also with the angular velocity. You're not going to use this, okay? You're not going to solve any problem with that. How do we associate a vector with the angular velocity? We use the hand rule, right hand rule. So I use these 4 fingers to follow the rotation. So here I'm rotating like this, okay? And my thumb indicates the direction of the vector. That's the convention. That's how we see. Okay, so here, if I'm rotating in this direction, okay, I just give you this vector, and you say, oh, she's rotating like this. If I gave you a vector like this, you say, oh, she's rotating like that. Okay, so it's just to give us the direction of the rotation. Okay, so the thumb.
So it's just up or down.
Up or any direction, right? If I'm rotating like this, you see the direction like this. Any you can rotate in any clockwise, counterclockwise, but the direction of the vector can be in any direction, in the 3D direction. Okay, what we learned now is conservation of angular momentum. Let's see if you can explain the demonstration. So, conservation of angular momentum, conservation of L. This is angular momentum. And now I'm putting that arrow there to say that angular momentum is a vector given by the direction, has the same direction as the angular velocity. Oh. Now comes the experiment. Can someone hold this for me? So just, you're gonna hold? Okay. So just make sure I don't rotate. So just hold. Now look at what I'm doing. I'm going to rotate this wheel. So it's rotating like this, all right? So you see that the vector that I associate with this direction is pointing down. Everybody agrees so far? Okay. So I'm rotating like this. Now you can let it go. Just, okay. Now look, I'm not moving, right? And then I start moving.
What? What?
Like magic. Why? What did I do when I changed the direction of the wheel? The vector, right? So let's try to make a drawing. Initially, when I start, my vector, my angular momentum, was pointing down, we concluded. So this was my L initial. Then, after, when I rotated, where did this vector go to? I pointed up, but I have to conserve. I have to conserve angular momentum. So how can I conserve angular momentum? I have to guarantee that the same initial remains later on. So how can I guarantee that? What happened when I turned the wheel? What happened to me?
the opposite circle.
I started moving in the opposite direction, creating an angular momentum here. So that the sum of this gives what I had initially. Isn't that nice? So it's conservation of momentum proved. Now you can say, oh, but if you do this on the ground, let's do it on the ground. Okay, so there it is, moment of the angular velocity pointing down, and then I rotate.
We have friction.
Friction. I can feel something trying to rotate me, but the floor holds me. Anyone wants to try this? Anyone is brave?
What is it? What do you do?
Wanna try? Come, Laura. Don't fall. So, don't rotate too fast. So, someone, can you hold it again? I need assistance. Okay, so, you see, it has very little friction. So, okay, so you hold this. It's a little heavy, and put another hand here. So this one, and try to not to touch yourself so you don't get friction. This one you rotate. Alright? Yes, rotate. A little more. Okay, good.
Do I keep going like
Keep it like that, and now just let it go. Now you can stop. Yeah, you can let it. Now turn.
Whoa! Yeah, I'm so surprised.
Okay, anyone else wants to try?
It's really cool. But don't be
Alright.
taken by
So,
surprise.
can you hold for her? Go. Open a little bit the legs to give you more balance. So keep it holding. I'll tell you when to let it go. So this one you rotate. Okay. Try not to touch yourself to avoid friction. Okay. Don't rotate too fast. That's good. Now you can let her go. Now you can turn.
Wow, it's so cool.
And now turn it back.
so calm.
And this stops. No, it's like magic. You can turn.
So cool.
You're so
Guys, I have a future in the circus.
All right.
I
So
definitely
this is going to be. If you want today, you can try. So this is the end of it. It's going to be there. It's going to be in the lab, so anyone can try. But try with someone else. Guarantee you don't fall. All right. So that's it. We continue next class. Okay. Yeah. For everybody who is here,